Okay, so I would like to allow to make questions during the talk, so not waiting for the end. So please ask when you like. Otherwise, it's boring even for myself, not for others. So please ask. So we will arrive to this. This formula here. So you remember, maybe I should remember what happened. Oh, wow. Even before there was not my. Also, I am distracted by my face. Okay, is it okay? Yeah, by the way, I cannot speak if I see myself. I think. But I mean, what's wrong? Okay, killer open. Okay. Okay. Okay, now it's cool. Okay, so we arrive here to this randomization group scheme. So you start with this decomposition, which means that you decompose the propagator in scale. So let me say that you will find some details in this book, for instance. This is called, it's an old book, but at least the introduction is by myself. At least the introduction is not perturbative randomization workshop. At least this, what I'm saying at the beginning is not updated, so there are no the latest results, but at least the general scheme is there. Okay, so this is more or less the rough idea of this dimensional group. So you decompose this covariance, and then you integrate scale by scale, and then you get another interaction which is different. So you get another theory. So this theory is done. So at the beginning you start with some monomials in the fields, and then you arrive with other monomials in the fields. So before the lunch break, we arrived to this argument that the propagator with a certain scale, with the cutoff up to gamma to the h, is equal to the essentially equal up to subligny term to the propagator with cutoff gamma n up to this factor. And then if you have this essentially, I mean, this is the heuristic idea, is essentially that the distribution of the fields with this cutoff is the same as the distribution of the starting point field with this prefactor. And then this means that this VH are similar to Vn, but with this prefactor in front. Okay. So now this prefactor was obtained very simply if you replace in O this psi with this kind of with this X. So you rescale again. Then when you rescale, you get this V, and then this term here is simply this one. Okay? So you have n fields, or n as n fields. So you have gamma h minus s d minus alpha n, and then you change variables here, and then you get the d. Okay, very simple. So it's simply, so this is the crucial concept in quantum field theory, is that what is called scaling dimension. Okay. So it's d minus alpha divided by 2 if the propagator is this form. Of course, it depends on the theory. There is something very basic. So what is interesting is that if now the terms with d positive, negative, or 0 behave in a completely different way. So the terms which d is positive increase, generating an organization group, so are more and more important. The terms with d negative became less and less important. And in fact, they are called relevant terms, the terms which has d positive, and irrelevant terms, the terms which is negative, and marginal terms, the terms which is 0. Okay. So a lot of physics is just encoded in this very simple argument. This is very the basic point of our quantitative theory. Yes, I mean this is the monomial. So of course you can consider a vertex. So for instance, now I am considering a theory only with a kind of phi. Of course, for electrodynamics, you need to consider two kinds of phi, and then this becomes a bit more complicated. So now I'm considering only one kind of phi, but then of course, if you have two kinds of, so in fact, when I said you can have fermionic and bosonic, but then of course, the basic theory, the quantum electrodynamics is both functional integral, which is bosonic and fermionic. So as I said, quantum electrodynamics is the most difficult theory. It contains the two kinds of functional integral together. So it's another complication. But for the moment, let me consider only one kind. So otherwise, the difference is very small. You will have another propagator, and then you will have the dimension of this and the dimension of the other, and then you will get that. In fact, okay. So as I said, so you understand this is a very deep point, but now you have to understand. So here this is completely general, so for all the possible theories. But now let's see which are the physical implications. So the physical implications are quite different if you are considering a statistical physics problem or a condensed matter problem, or instead a quantum field theory problem. But the difference is which is, if you consider, maybe it's written here, if you condensed matter, then the problem is only the infrared. Okay, so you only need to integrate negative scale. So this large n, which is the maximal energy, is fixed. You can fix it n equal to 0. Okay, because in that case, the gamma to the n is the lattice set, and the lattice set in condensed matter is fixed, it's 1. So you have n equal to 0. So the problem is simply to integrate the scale from n to minus infinity. Okay. So then you are happy if there are irrelevant terms, because it is a subjective point. So in a sense, the theory is simpler if you have irrelevant terms, because this means that the interaction becomes smaller and smaller at large distances. Okay. But if you want to consider instead a quantum field theory problem, the problem is the opposite. You want to send the lattice set n to 0, so n go to infinity. So if this decreases, then in the other direction, it increases. This is the reason why. The reason why this looks a bit not very intuitive, right? If you have a relevant term, which looks innocent, and then the theory is non-normalizable, because non-normalizable is a term referring to quantum field theory. It decreases, but if it decreases, it's bad, because if the coupling decreases, if you want that your scale is order 1, then must be infinite at the scale of the high energy, okay? But instead, if you are studying condensed matter, it's good, because you start with your microscopic model, and then you go to your observation. Okay, and the opposite for the other. If it is relevant, then it's super normalizable. So it becomes larger and larger at small scale, in the opposite direction. So when you consider large distances, it becomes stronger. But when you go to small distances, it becomes smaller and smaller. Okay. So in this sense, this says you that when this difference from 0, it's very difficult to construct a theory in which you have relevant or irrelevant terms, because in one direction you have problems. So there is also the case in which the n is equal to 0. This case is called marginal, and in a sense it's the best case, but it's very rare. Okay. Okay, so this is more or less the, so just to understand the situation in, for instance, quantum electrodynamics, which was the theory we were considering, is something like, no, sorry, this is still not finished. Maybe there's another slide. Ah, yes. Okay. So this is just the dn. So the base situation is when dn is, for the, is marginal, so you have 0. But then still you have to distinguish two cases. So this is are typically the physical theories in quantum field theory, in which the dimension is 0. So the theory is called renormalizable. In this case, you have still to distinguish, because now you have that, I will tell what these things are, this is just an introduction. You will have this, the effective coupling of the theory, verify equation like this. So the dimension is 0, but this is a dynamical system, and still the coupling can again decrease, increase, or remain bounded. So one can distinguish between marginally marginal, marginal irrelevant, and marginal relevant case. So maybe this is a bit confusing if you have not seen before, but I mean, before I am considering the dimension of the coupling. The dimension can be of the interaction, can be positive or negative or 0. Even the case equal to 0 is not, you have to distinguish cases, because still it can have a change iterating renormalization group. But the physical theory is typical when you, maybe you have this term, renormalizable theory are marginal, the coupling is 0 dimension, but then can increase or decrease with the logarithm extension. Okay. Okay, well, I will tell more later. And then, okay, now, of course, it's impossible in 4 hours to speak all the possible cases. Running coupling constant, which have not been defined, so I will do it later. Okay. So maybe, okay, maybe I can skip the story. Maybe I can consider just some application, right? So to understand, I will skip the story, I will do it later or never. Okay, let me consider just some applications. Okay, so this is an application of, let me tell you an application to these ideas which I like, which is an application to graphene. Okay. So, so this is an application in condensed matter. It's an application to condensed matter. It is an application to transport coefficients that are related, I think, to the lecture of Oise. I think you will speak about transport coefficients, maybe, or all conductivity. Yeah, I know, but at least, no, yes, I know. But for this, think about conductivity, so you will see more in detail what is conductivity. So I don't want to introduce too much, but not graphene, but at least the conductivity you speak about. So this just to say, because this functional integral will be sort of general stuff. So as I said, so this is the model. So this is written again in second quantization. So I hope everyone is familiar with second quantization formally. So what means this? So this is called the Hubbard model on the honeycomb lattice. So you have an honeycomb lattice. So that is so why I choose this, because this is the physics. I mean, this graphene is obtained by graphite, and graphite is done from carbon. Okay? So this is what I call side binding model. This H0 means you have the hopping from X to X plus delta. Delta are these two vectors. And this is simply the interaction. Okay, so this is the local interaction. So it's called Hubbard interaction. You have this is essentially the ultra local interaction. So this is the model for graphene. And as I said, if you neglect the interaction, then this model is solvable, quadratic, and then you will get, you can pass to Fourier transform, you fit Fourier transform, and then you can write this in terms, you can compute the eigenvalues, this is obvious, and the eigenvalues are exactly this picture I showed you before. Where is it? I found it very quickly. Okay, this is the eigenvalue. It should be found. Okay. So if it's just a computation, it takes 5 minutes if you want to do it. Very easy. I mean, if you simply pass to Fourier transform, then you will get a function of k, which is something like 1 plus e to 2 pi over 3 and so on. That if you plot, you get this. Okay, it's just simply the eigenvalue. Yeah, this if u is equal to 0, is 1 page, okay? Then you can compute the conductivity of this. The conductivity of this is pi over 2, okay? And now the problem is, what happens if you add this u, okay, this Hubbard term? So of course you can try to make a perturbative function. So you write. So the story is that you should write in second quantification. Then you will have the trace of the Gibbs factor times something. Then you can show that the perturbative expansion of this is that can be written in terms of Grassmann integral. So you write directly in terms of Grassmann integral. At the end, you can expand in U, and then you get a series in U. Okay. So and then you compute order by order these terms, and you see what you get. Okay. So if there is someone familiar with this graph, then you start with the exponential, then you get and then of course you want to talk to the conductivity because the PGA2 about this extension of the validation. Then you can see it. That's not very important. I will not way that I will comment that people that know a bit about the function written in terms of graph. Okay, so now the point is no one last is no consideration. But then when you do that, it's what you find on the flowers. So, you know, it's very short, you can do it with these things. You can get any so the point was that experiment that they showed you studies that all this the results will be what all these are certificates. So all these are very small. So this was an example of the device in which Mathematical physics can really give an answer because there was this debate. This debate is not completely settled because as usual, if you give a theorem to physics, of course, the theorem has condition. Typically, these conditions are not exactly the ones that are needed for the experiment. So the question that I think is we can prove this theorem that was give a sort of solution to the at least in certain case to this apparent paradox that there are these huge corrections which were not seen. Maybe it's useful at this point to show you the data because I think I'm very happy with the result. It's a bit more. Maybe I can increase. I can try. Better now. Okay, you see. So this was the. Here is written theory, but the theory without interaction. But indeed, this U is one. So how was possible that the result was, so when Games and Rover write theory, they mean this. But that poses a problem because the prediction, how the prediction done without interaction was correct in the experiment, which was known that the interaction was present. Also, let me say that in the experiment, some other quantities were changed by interaction. Only this conductivity was not changed. So that was strange. So this is the theorem we proved. This is one. So you can decide if this gives you a solution to the problem or not. It's much. I must keep everything. Okay. Okay. So now let me say again, all this. Okay, so I want to excuse because all these sentences, I mean, you can, it's like using all of the sentences you can click, then all of the sentences is what to prove. I mean, this is what is called Kubo formula, which is again a very difficult problem. There is a big rotation for this, which is also a problem. So let me keep a number on the page, otherwise I will not finish. So accept this. That the conductivity, that maybe I or other talks will come back, is essentially the correlation of the current. I should define the current. The current is defined simply by the conservation law. So you consider the density, you make the derivative, you have the commutator, then you define in that way the current. So you consider the average. You don't ask me why. I mean, this is called Kubo formula. If you don't know, maybe. Calculated, but anyway, the conductivity, what you measure is expected to be this, is the average of the current, but then you have to make this limit. You have to divide it by P0. So this is the Euclidean, so you have to prove big rotation, which is possible to do. But then the point is that very important point is the order of the limit. Okay? So you have to make first the limit P going to 0, and then P0 going to 0. P is the space times of the Fourier transform, and P0 is the conjugate variable of the to invert the relation. So this is very nice because usually people tend to think that the change on limits is not very important. This is crucial. All the theories so a lot of almost all these thoughts in regards to problems of the change on limits. Let's remember this also. Okay, so the theorem we proved, it's proven already 15 years ago. It was the thesis of Marcello Porta. Is that if U is small, then the conductivity is exactly the one of the non-interactive. So there are no corrections. So you could say, like maybe there is no U. No, for instance, other quantities like the velocity, it is the amplitude of the cone. It changed very much. Changed by order. So if you look to the result for the first time, you say, it's very strange. But this is exactly what is later. That the conductivity does not change, and the velocity changes. In fact, this is exactly what is observed. See, maybe I didn't think. Here it is. Yeah, in fact, this is also, yeah, thanks. This is a nice calculation. Why I could put equal to 1. But why didn't put T equal to 1? Because it's already interesting that the conductivity in the non-interactive state does not depend on. In fact, it's pi over 2, not pi over 2 times T. It's really pure number. So even if you put T here, you always see you get pi over 2. So that in fact is more, that in a sense, one needs to understand already why it's already non-trivial why you get pi over 2 without T. Non-interactive. Okay. So, but then this remains a pure number. So what was a pure number remains a pure number. The velocity, which was not a pure number, is a number. So in this sense, maybe it's less of that. Yes. Yes. Okay. So in fact, this it was exactly my comment. One is never hated. Also, for no, I mean, but when you prove that, of course, no. But I'm not saying because of what when you prove that, can I be proud and say I explain finally a physical phenomenon? Well, I don't know because U is small. Maybe when you do it for I don't know. Maybe we should have to put what you put 1 over x minus 1. That's T. No. So that is long range and order 1. And in fact, the discussion in physics regarding that now the theorem is accepted. Because the story is like that physicists are interested in the case in large U and long range. But then they were trying to make the computation in this case and they get something strange. But in this case, it's surely in there. If it results remains like this long range interaction or the U, I don't know. Maybe at this long range interaction we should start. That is difficult because the expectation is unclear because the experiment seems to show that it's there, but it's actually the experiment and then yes, the experiment show you that it's even with long range interaction. So I think that the claim would be that if I put 1 over x and expect your Hamiltonian, the result should remain. But now, if you see from the proof, that is, but it's not impossible. So anyway, now these results, at least, for instance, if you take this book of Katz-Nelson in graphene, it's the only, it's quoted, I mean, because at least explained experiments in this sense. The question of the conductivity in graphene for short-range interaction is fixed. If this result remains true or not. Also, people is very much interested, maybe I like to speak about experiment, but even people is not very much interested in the limit, but in the corrections. I mean, this, so even, because this is the limit, so the limit is this, but you see, if you go in the frequencies, you think that there are, so even this is something interesting, how much is the correction? So this kind of measurement is called optical conductivity. It's not conductivity. It's the conductivity with some sort of electromagnetic statement. So they change the frequency. So this curve is the function of the frequency. So I take the limits and considering only this point. Then it would also be very interesting to go there. There is a lot of debate on this. There is, I think, is a very nice problem because it's, the experiments are clear and the results can be done. Also, let me, okay, so, but I want to tell you just the idea of how simple it is. So, of course, in that way, it's impossible, of course. Okay. In that way, it's impossible. Even this graph, so there are some fields who put this a complete computation. So this graph is simple, complex, the passive one of it. But then the result is a steady state. So one would say, well, I have to really consider something. To the time, you have to say the final axis and the computation can be done. So it seems impossible to prove the solve this contribution of course. So of course you don't have to find. So the idea is this, I tell you because it's so also let me add this comment that so this result looks very similar to universality results in the whole effect. But as far as I know, there is no topological explanation for this. So usually ask people like standard approach. I think it's possible. Looks strange that at least in the non-interacting case there are no abstract proof, topological proof for that, but as far as I know, we are. I mean, our approach is brute force, just focus together. So it's very tempting, despite that, it should be some risk, but no one. So one could say, which is the difference between this theory and all the facts that I will show you later? This theory is critical, so the propagator is singular, instead in the all effect we have a guess. So this, I think, this result calls for some benefit. So anyway, let me tell the proof. This is very simple. So it's very simple as if you accept some statement that is false. So first of all, we write in Grassmann integral. Okay. So now there is a technical part that I will speak about that tomorrow. So how you can control this Grassmann integral. So for the moment, I decided to proceed in this way. First of all, I tell you what is possible to prove, and then I will tell you the technique instead of the control. So suppose that I can prove what I will tell in a second, and then you will see. So now you have, so the crucial point is that we want to show that the series are convex. So that is very important. They are not power series, but then you can prove convergence. So it's, in the sense that it's not true for any use or any this. So now the argument is incredibly simple because this is one. So if you look to the expression of phi is even, you see immediately because there are two propagators which are. So if as it is even, so if you look to this looks very much to a derivative, right? So if a function is here, the derivative will be odd, so the limit will be 0. Okay. So one second, but we know that in the free case was phi over 2. The point is that the function is non-differential. So this is the only way out. The function, so if the derivative does not exist, depends on the order of the limit. So if the limit exists, it would be 0. But the limit does not exist, depends on the order. And this is already, you can see this already in the case of the free case. The free case is already this phenomenon is already there. And so you get phi over 2 because this function is not differentiable. Because you know a priori that this is even, okay? So this is the reason why it's so important to divide to the order of the limit. So the order of the limit, the result, the function is not differentiable, so it depends on the order. So you have to make the limit in the correct order to get. Otherwise you get. So now all the point is this, that you can make a composition, and this is really an outcome of this randomization group analysis in two pieces, one which is simple and the other which is very complicated. Okay. But the simple part, KA, so if you remember what we said, so maybe I should add another thing which is important. In this kind of theory, the dimension of U is negative. Okay. So the interaction is irrational. So it becomes smaller and smaller. In fact, if you make the computation I did before, you put alpha equal to 1, d equal to 3, you will get 3 minus n. So if n is 4, it's minus 1. Okay. So the interaction is irrelevant. So the interaction becomes weaker and weaker, but it changes. So the fact that the interaction becomes weaker and weaker does not mean that it does not contribute. It means that produce finite normalization. Okay. So the interaction is irrelevant. So now you have marginal terms. The marginal terms, however, are the quadratic, or the relevant terms are the quadratic, or the current. The current is marginal. But so at the end of the story, just to give an idea, the point is that you can make the composition in this way. You say this term here contains only terms which are marginal or relevant, and this term contains at least an irrelevant term. Okay. So now this is what is this? So you can prove by the elimination group, or maybe I will try to explain better later, that this is exactly the free case with the parameters changed. Okay. So here is, and so if you look, so this is exactly, if you remember last hour, in which I introduced this concept of bare and rested objects. You see, this is equal to the free case, but yes, the velocity, the amplitude of the cone is changed. It's renormalized by final cruising. In the same way, the vertex, the resistance was about to change. This L, which is the renormalization of the vertex, divided by Z. These are all series. Okay, so all quantities are normalized. The vertex is normalized, the wave function is normalized. So this is not the free theory. It's the free theory with something normalized. Okay? And this is like the free case, so it's not differentiable. So the second term instead is a complicated, it's a very complicated series of terms, but now it's differentiable. Okay, all the point is this. So if you have at least an irrelevant term, it is differentiable. So as it is given, so now we have the third element, which is very important in this story, what are called word identities. Word identities are essentially relation between correlations that imply something. In particular, they imply that zeta 0 is equal to Z, zeta 1 is equal to 2 is equal to BS2. Which is this. Okay. So this is called word identity. So in other words, all these Z are series, very complicated series, but you can prove this a priori, you can prove this relation between them. Okay, now you see the miracle happened because this term then is differentiable and then it's vanishing. This term is equal to the free term, okay, with the velocity change, because now this is essentially df, but this is the average respect to df. Df is like P. So we know that the conductivity was not dependent on P. So even df is we complicate this A non-zero, but even if it's non-zero, then the result of this integral is pi over 2. So and this is done. Okay, so it's finished. Okay. So you get only this, but this is independent. At the end, with this strange, with this complicated entity, this is exactly the idea. Of course, I would say it's impossible to see this interpretation theory. Because it's not true that it remains only the case. You have to extract from all the terms at any order to reconstruct this, and then the end. I don't think it's possible to see this process. It's possible, surely, in some finite order if you make very careful internet. So that means that this is exactly pi f over 2. Okay, an extension of this argument was proved for Gauss conductivity. Gauss conductivity is something similar happens, but it's simpler because there is no need of multi-scale analysis because there are no gaps. There is a gap in the scale, so you can consider just sort of equal scale. In this case, you have to perform a full convolution. Also, there is some subtle point on this. You have to show that the conductivity which we can take them in this way is the same as the conductivity defined for real time that is possible to do. So this is an example of a relation group. Let me say that, but let me say a comment. I mean, the fact that the velocity increased, there is a nice experiment of 10 years ago in which they see that the velocity increased a lot. It's at least 4 times. So apparently U is very big. They find cases in which the velocity 3 times the delta. So there is a stronger. Despite this fact, the conductivity is universal. In fact, this assumption is justified with I don't know. I think there are no other ways to. But I think it's a nice example in which you can show that some mathematical argument really is in agreement with it. Okay, so but of course now I've hidden all the possible technical details, which are here. So how one proves that this kind of thing. So how you can control all these functions. So I will improve this decomposition, but I want to give you an insight on why once you have these properties like that, the focus. So of course, this decomposition is something that, which is very deep and really can be understood only on the transition group argument. So maybe I can show you another example. This is much more recent. It's a paper we are still writing. So now let us see an high energy result. So you will see the techniques are very clear. So let me consider now instead the things that I was starting from. You remember I started from this geomagnetic factor. So let me see how similar ideas can be applied to the geomagnetic factor. And I will give more details, so you will see more and more technical details now will arrive to this kind of thing. Okay, so now why so now so you have to understand this point that in the case of graphene, the lattice is given by the part, which is the ion. In the case of quantum field theory, this lattice, you have to put the lattice to give a meaning to the theory. Otherwise, the theory, as we said, is trivial, so it's probably has no meaning. So the lattice in this case is what is called an ultraviolet. You have to essentially say the theory holds up to a certain state, and we are saying that the theory cannot be the limit A equal to 0 okay, because otherwise the theory has no meaning. So is this a problem? Not really. It's not. I would say it's not a problem. It's not a problem. So in the sense that there is no problem with the cutoff in quantum theory. On the other hand, you have to prove that finding quantum theory with the cutoff, then the result is equal to the result without cutoff. What the experiment asks the correction. That's the cutoff. You have to get good bounds. I mean, you have to show that there is, because in the difficulty, the cutoff in this way is something okay, put the cutoff. Then after the cutoff, you can take noise to value. So a lot of people but there are no sign of solution of going to value and so on. But if you use correction, are not usable. You can use it in universality argument whenever we regularize the theory, the result is. But it's not worse. It's a technical problem. We have to show that the result is equal to the result without cutoff with correction, which are very small in a physical region of the problem. So that's the issue. But I don't think that at the moment there are no other ways to define the quantum field theory except that. I mean, this is what is called the effective point of view. So in fact, so that's okay. So this was so let's make the whole comment about that. So now you have trust to say now it's potential. This is called this from bottom to the after that after the world. Of course, you can complicate more and more the theory, and then but at the end, I think you never reach anywhere. The other possibility is okay. Let us consider this subset of the theory, for instance, about Oise. That's it, and then I would like to define that. Of course, the other thing, pure is belief that it is possible to construct. And then what happens in one matter? Then maybe there are other fields, and maybe there are fields, who knows? Right? But if what I want to do here is something simple. What I want to do is simple as possible. Quantum field theory with the cutoff, and we get an answer. So for example, now I'm considering, so of course, if Younger myth is believed, I don't know, now maybe it's totally like this discussion, but Younger myth, pure Younger myth, is the Nobel Prize of growth and the discovery of so that maybe is a fourth dimensional quantum theory, but it's only for one. For growth. But the growth, I find very strange to be possible to construct first the fluence and then or the strength, right? I would say it's better to first construct the non-relativistic quantum mechanics, then the relativistic, then, okay, to go. So a strength that you say you have to find the most difficult possible, it's because it's non-perturbed, but it is a lot of other problems. I follow this other stuff. I mean, I put the cutoff and I want to prove that, you will see what I want to prove. I want to prove that the results are independent on the cutoff. Okay? So that's, I would say, would close the story. Then what happens beyond the cutoff is a border. I don't have any problems with it. Okay? We don't know gravity, strings, you know, so never know. Okay? So the cutoff means simple. All theories should be at the end effective and valid in the domain. Any theory is valid in the domain. Of course, Navier-Stokes equation are not true in whatever scale. Any theory. So the cutoff means simple. The theory holds up to this level, and that's it. Okay, let's see. But then you say, okay, put it off, everything is easy. No, this is all, because now there are two conflicting points. From one side, you have to take the cutoff very large, because you don't want to see the cutoff. So if you have an experiment at a certain scale, and you want to, you don't want to see the cutoff, so the cutoff will be much higher than the scale. That cannot be too high, because if it's too high, then you have to remove it, then it's down. So the problem is that you must find a way to avoid these two things. I mean, you have to take it large, but not too large, because if it's too large, it's impossible to take it too large. Otherwise, it would be useless to introduce it at all. So it is possible to construct a theory with this concept. So that is the problem. So let me also say that there is a relation between the perturbative emissivity and the maximal cutoff. In non-normalizable, one expects power, while in renormalizable, it's expected exponentially large in the So, of course, in a normalizable theory, you expect this exponentially large in the inverse path. So this, if you remember the number which was quoted by Mordini, so this R, which is 1 over 1/7, then this means exponential of 100%. So that's no problem at all. Instead, if you get this, you are not so happy, because you get the power of 137 is much less. Also, let me make a comment on this on Fermi again. What to indicate? So before was indicated the Thomas Fermi theory. Let me indicate the Fermi theory. Fermi theory was a non-normalizable theory, but non-normalizable theory means simply that you can get cutoff up to an inverse pattern, which was very perfect for the experiments of the time. It depends on the energy you can reach. For the up to the 50s or 60s was perfectly good. Only after the other experiments that you need more higher cutoff. And then I will comment about that. Okay? But then again, there are other problems related to gauge theory, okay? Because of course now you cannot use simply the perturbative arguments I was said before. So anyway, so which is the so to make this story short. So let me consider the model I want to consider now. How much time I have? An hour. Not half an hour. No, it's not half an hour. Okay. Yes. No, okay, it's written there. Okay. So now if the model is with 2 feet, yes. So you have that. So this is the model. This is right, more or less. You have a boson and a firm. So this is a double function. But I mean, this is a bit. So this is a Gaussian measure. This is the fermionic measure, and this very complicated interaction. So this interaction is the boson with its size, and these are external fields. Z is a real field. So of course, in a moment I will integrate this P in the Z. I will get so P in the Z. So the propagator of this is this. So it's linear plus the mass with the cutoff. Now the cutoff is a function which is 1 up to gamma n and 0 n. The same for the propagator of this. So this is regularized version of the Vision. Very close to quantum electrodynamics, except that the Z is the mass and the coupling depends on the chirality of the formula. It's very close. So if you put instead of lambda x here a lambda, and then n equal to 0, this would be so you could say, well, why you want to consider this more complicated weak forces instead of the simple it's even more interesting. For example, well, the reason is that I have this mass here. Otherwise, I have to this singularity is very difficult. But on the other, I wanted to consider a real physical problem. So these exist. These are what are called the neutral weak forces. So you one set of weak forces. As I said, the contribution of to the geomagnetic factor of this term were computed in the 70s and by Weinberg and Jekyll, and show you the example. So it should be a simple way to do that. I like it. So this so in perturbation theory, this was the computation of Jekyll and Weinberg of the Z contribution to the geomagnetic factor. So they get m squared divided by m big M squared times this volume. Okay. So this m is the mass of the electron, and the m is the mass of the Z, which was measured over. M is the mass of it. So I don't want to consider something that does not exist. I want to consider a reality. Okay. So of course this would be much more interesting, and not say not that, but it is much more difficult. That this is simpler because we have this M which produces everyone but this at least so of course the M is like every another. So the mass of the electron is essentially is almost zero. So it's very important to remember that for me, M is much smaller than this large M. In fact, our result could be, we could even send M to 0, but if we send M to 0, we get 0. So M is, but remember, M is a very, very small parameter, and M is not. But that is not unreasonable, because M over M is 10 to minus 6. Also remember, so I want to put these numbers because I think without numbers, there are a lot of mathematical results which are a bit useless because if you don't stay in the correct region. So also remember that lambda is related to the alpha, and alpha is also small. It's 001. It's 10 to minus 2. So it's still small, but much larger than this. So remember, so the energy scales are the coupling, which is 10 to minus 2, and then small m, and large m, which is 10 to minus 2. So this is the region I'm thinking about. So now the problem is, so what we want to prove is something like that. Suppose that so this is the result of Jekyll and Weinberg truncating all the higher orders. Okay. But so how we can bound these higher orders? We know that the series is there. So a comment is even not normalized. To consider only the Z, so even not normalized because the anomaly is not the count. So it's even not normalized at all. So if you want really to consider only the theta mass, you can keep only this effect in front of you. So what I want to find is that I want to consider that regularized model with the lambda and m. I would like to get upper and lower bound for the A in terms of this field. I want to show that in a suitable region of the parameter, the result is very close to the Jekyll and Weinberg result, even if the series of Jekyll and Weinberg is not. So we want to get an upper and lower bound. These are things that explain why the prediction is correct, even if the series is determined. Okay. Okay, maybe of course, only 5 minutes. I will not go in details on the definition of the model, which is this, but I tell you what I'm saying in work. So the result with an announcement is in the physical review paper, and then in preparation with the application, which is my student here. The result is this, that if you consider the full model with this cutoff, so lambda is fixed now, then this regularized geomagnetic factor, which you have to define, is equal to the Jekyll and Binder result up to R0, which is the mole in this M, and this R1, which contains all the possible higher order corrections, which is smaller than 1. You can take it smaller if you want, provided that lambda over M is greater than 1 over epsilon, but smaller than epsilon divided by lambda square log square of n over. So this means that you have to take this large, then lambda has to take a small, so you can ensure this condition. The smallest is lambda, the greater you can change. So in this fixed precision, then you will have. So this can be ensured. Of course, now the lambda obtained in this bound is probably not realistic. But look to a very important factor is this presence of the loss. So all the difficulty of the analysis, you will see in a second, is the following one. That's a few, and then I will stop. I will tell you about that later. Okay, so in a sense, this explains the paradox why you get the first order result is correct, even if the series system converges. I mean, you can put something that it's closer with any precision, provided that you can verify this. So let me say last important comment, that maybe escapes you. So all the point is that this lowest order is proportional to m over n. So you have to prove that this m over m is all orders in perturbation theory without destroying the convergence. And in fact, we can prove that. So here we have a log. So you see the log is R. The log of 10 to the 6. But if you make without cancellation, you don't get the log. You get n over n, and then that's so it's very difficult to put the log. So all the question here is a question of log. This log is very good. This, however, is not good because it's 1 over lambda square. Lambda is small, but not that small. But if you can replace this with an exponentially large, which was people expect, so people expect in the full standard model a bound like that, in which this is replaced by that. This would be, so then if you put 1 hour over 137 would be okay. So, okay, I mean, there is, it agrees with the experiment. So even if the series is not convergent, the result is close to the lowest order. So the point of view is this, that we want to show that you have a series which is not convergent, but the result of the regularized theory is equal to that up to a correction which you have to tell, which you can take as small as you want, provided that you are in a region that verifies it. So maybe I can continue. What is called now electroweak field? They call it electroweak. Of course, they consider also the data. Because the data and the in fact, you know, the minor point they get introduced also in the neutral part. The neutral part is actually, they brought the paper because they wanted to imagine that it was possible to predict the date and system right? But it was known that the W is not the neutral part. Then later, And then it was often that causing was no, no, I have only the Z. Okay. The Z, I mean, there are two, yes, because there was a math. And this is protecting. I know that why you don't do the photo of what for the because at least here I have a big math, the math of the Z is yeah, it's a math. Yes, but it's I mean, nothing is free here, so you see the math is not, but it's silent, so it's very good. So, in a sense, the theory was never the math, but anyway, but we found better for the math, rather than but anyway, it's like it's kind of because you see here, you see, yes, this is exactly the Z. And you see, if there is lambda X, only that. I mean, the massive boson would be lambda. Only this. This seems nothing except it's the equation because it breaks the symmetry. So this is, so you could say, it's a very innocent change. It's not because if there is no lambda, then this is the gauge. You can, in quantum electrodynamics, there is a gauge invariant, right? You can change all the particle fields with the phase. Here you have to change it, with a different phase, the two components, the two chiral components. Yes, yes. I could add also the W. Yes, they make it. Yes. In fact, I'm not calling. I call it the neutral sector of weak forces. Yes. I'm very modern. Find something that I can find up and down. So this is the neutral sector of weak forces of the standard model. In the Euclidean with the double. And even this, but at least for that, I can prove that this truncation is, in a sense, correct. Even not this is true because I don't like this 1 over lambda, because the 1 over lambda is simply 137 squared, but its epsilon is small, so it's not enough. But right, this is small, but this is very small. It's not also I have these constants which are very bad, so I'm not sure that. So I know if I put here the real value, this is not greater than that. So the real lambda would be much smaller than 1 over 37. But people believe that here you could put exponential of 1 over lambda if you add also the W. So that would be the goal. I mean, to get here. So another possibility would be to consider maybe, yeah. There is, want to consider realistic theory. So if I consider quantum electrodynamics, I don't have the N. It's another, so there is no mass, so it would be even worse. But at least this is, I think, the first result in which you prove that the truncation of in the standard model, you can give upper and lower bound, because you can take epsilon 1 over. It depends now on the experiment. Yeah, depends on the procedure. You want to say this do 10 to minus 3, then you put here 10 to minus 3. And these your parameters, you know. Even that is, no, it's more complicated because the neutral sector alone is not believed to be normalized. But if I introduce the gluon, because there is a phenomenon called anomaly acceleration. So you have to put really the gluons and the electrons. Then in that case, people are expected. So it must be normalized. So it will be, for instance, one effect. It will be, of course, it's normalized. But then you don't have them. In this case, if you want to have them, then you have the two. So maybe it's better. I don't know what it is, but to try to eliminate the M. I don't know which is the best thing to do. To eliminate the M and to get it to a lambda, or to add the W, keeping the M. But anyway, at least. So this kind of bounce, by the way, it's the typical one of non-normalizable theory. So if you consider Fermi theory, you get that. I'm not really able to use the 1 over k square of the known locality. So that's the the theory of favor was not normalizable, and this is the power counter of not normalizable theory. So QED is expected you should get to the lambda, then would be no paradox. I would say then would be everything would be safe. So QED would be an effective theory holding in range of parameters and the spreading of the because this exploration still would be usable. So that's what the philosophy answer.